Hi, good evening, students. Welcome to JEE Amrita crash course. So we are starting chemistry class today and with some beautiful questions. Okay, I hope everyone is ready for chemistry class, right? Are you ready? So if there is any audio issue or video issue, please let us know. Everything is clear, right? Audio, video, clear? So meanwhile, I'll be checking your text. Okay, if it is fine or if any doubts, no. So I'll go through the chart also. Okay, fine. Everything seems to be fine. Okay, so we'll start here with this question. So look at the question here. Which of the following is not expected to be intermediate of the following reaction? So by looking at organic reactions, no, we should predict mechanism. So do you know what is the mechanism here? What is happening here? Basically, see, this is our reactant. Okay, look at the reactant. Left side to the arrow is our reactant. And this is our product. Correct? One second, let me clear this. Is it visible? My writing? One second, one second. Some technical issue. One second. I'll get back to you. One second. So this is our reactant. This is our product. Okay. So what is happening basically here? See, one iodine is replaced with OH, but not in the same position. Okay, but not in the same position. So what reaction is this basically? Because organic reactions, no, there are different types. Let me write those types of reactions. There can be substitution. One group or group of atoms replaced with another group, that is called substitution. Okay, or elimination type. Okay, or addition. Okay, or rearrangement. So these are the four types of reactions. Okay, now what type of reaction it is? In these four types, the most common. Screen is not visible. Are you sure? Everyone able to see the screen? Yes, right? It is visible, right? Okay, okay, fine, fine. Okay, thank you. Okay, fine. See this? It is substitution. Okay, it is substitution, no doubt. Okay, so if it is substitution and this iodine is replaced with H2O, and this is basically, you know, nucleophilic substitution. Iodine is replaced with water. Fine. Now see this carefully. See this carefully. And it is water and alcohol. You can directly write, no, most of the cases. Substitution nucleophilic. Fine. This is called SN1 reaction. Sir, what is SN1? SN1 is basically, it is nucleophilic substitution, but one refers to first order reaction. Okay, it is first order. Sir, how do we know it is first order? Yes, I'll tell you. There must be weak, very weak nucleophile, like water, alcohol, most common cases. Solvent has to be either water or alcohol. Okay, easy way to predict SN1. Okay, and also because water and alcohol are called, no, they are weak nucleophiles. weak nucleophiles, they favor SN1 reaction, and there must be carbocation formation. Okay, so there must be carbocation formation. Okay, if there is carbocation in any reaction, rearrangement is possible. Rearrangement means what? The molecule will rearrange to get stability. So all these are SN1. Step by step now we'll see. Our reactant is this. Okay, so in any SN1 reaction, what is our first step? First step is breaking of this bond. Okay, see, what we'll get is this positive charge. Okay, step by step we'll look into this detail, okay, of this mechanism. Fine, this is what secondary carbocation, I can say that, right? Do you know what is secondary carbocation? Carbocation means carbon with positive charge, right? This is connected to two carbons here. See, this is connected to two carbons, so that is secondary. Okay, fine. Now what I'll do is I'll shift one of the H minus adjacent to this. Said, but there are two hydrogens. Here also there is hydrogen, right? Okay, so let us, what we'll do is I'll change the color. Okay, let us say this is green color. Okay, and this is red color. This is red. Okay, and this is green. Which one I should shift? Can you tell me this? Because any H minus I can shift, no? So always any system moves in a direction to get stability. So which hydrogen I should shift? Green one or red one? Red one I'll again get secondary. So it is pointless, right? So hydrogen must be from green, right? So if I shift green one, so what I'll do is I'll shift green. So this will rearrange to tertiary carbocation. Okay, so there is red already there. Okay, and there is a green. So now I'll get positive charge over here. So this is tertiary carbocation. Tertiary carbocation. So secondary is there, tertiary is there, and now is there any other way? Can I shift any other hydrogen here? Let me write no other possibilities here or here. Any blue hydrogens can I shift now? No, because any hydrogen if you shift here, H minus shift, this is called no H minus shift. Okay, secondary to tertiary, fine, but tertiary cannot become primary. Tertiary cannot become again secondary. Unstable, any system no always move towards stability, not instability. So it is not possible to shift any hydrogen. So what I'll do, next step is this. Next step is this is plus charge. Okay, and water will give electron pair. Okay, so now what I'll get, this is donating electrons. O plus, one electron pair is donated, and there is hydrogen and hydrogen. Okay, fine. So look at all those intermediates. Now which is the correct option? Which is not formed in the reaction, which is not expected. See, look at the question now. Which is not expected? What is the answer now? Primary is not expected, right? So which is primary? This is not possible. Secondary, yes, possible, right? This is our answer, which is not expected. So this is possible, this is possible, this is possible. B, C, D are possible, but A is not possible. See, look at this clearly. I hope it is clear, right? Then option E. Any doubts here? I hope no doubt. Okay, so we'll go to the next question. Now, same SN1 reaction. Now, which of the following alkyl halide undergo rearrangement? Where rearrangement is possible? Can you quickly find out? Acha, explain it again. See this, the last question. So what I'm doing is, it is SN1 reaction, I know, because water and alcohol SN1 reaction. First, you have to break carbon halogen bond, okay, plus charge. Now, secondary to tertiary possible, yes, by shifting H minus. But after getting tertiary, you can't shift any other hydrogen which doesn't give stability. You can't shift these blue hydrogens because they don't give stability. They don't give extra stability compared to tertiary. So the carbocation will stop here, this major, and water start donating electron pair. Okay, so that's why O plus we get. These are all intermediates. So final product is given, right? So H plus will leave and final product is alcohol. Okay, look at this now. Which of the following alkyl halide undergo rearrangement in SN1 reaction? Where rearrangement is possible? Means always think about the next carbons, whether rearrangement is there or whether you get any stable carbocation or not. So first one, look at this. I'll break here. Okay, put positive charge. So this is secondary carbocation, right? Will it shift to tertiary? Yes or no? See, I'll write CH3, CH3. You can shift methyl group also. Okay, you can shift methyl group. See, I'm shifting. I'll show you the shifting with different color here. CH3. Okay, already there is one hydrogen and there is CH3. So this will give me extra stability because this is tertiary carbocation. It is stable by hyperconjugation because see, alpha hydrogens are there. These are alpha hydrogens. Okay, so this is stabilized by hyperconjugation and also stabilized by inductive effect. This is more stable. So that is why rearrangement is possible. Yes. Okay. And option B, what you have to do first step, you break this. No, there is a plus charge. It is secondary carbocation. Now see this, if it is secondary, so what I'll do is I'll shift one of the hydrogen from here. Let us shift, there is one hydrogen. Okay, I'll shift this hydrogen. I can write a positive charge at this point. This is tertiary now. See, secondary to tertiary. Yes, it is possible. It is stable. Again, it is stabilized by hyperconjugation. It is stabilized by inductive. Okay, there is no resonance here. Okay, there is no acha here. Okay, option C. Yes, option C. Fine, right. So option C, what I'll do? See, I'll break this. Okay, secondary carbocation. So what I'll do here? There is a positive charge. Okay, but if I shift one of the hydrogen, there are two hydrogens here. Okay, there are two hydrogens. You shift any hydrogen, you will get again secondary, but there is extra stability with resonance. See, if I shift this, what I'll get? I'll get allyl carbocation. One of the hydrogen is shifted. Okay, it is secondary, no doubt, but it is stabilized by resonance. Pi electrons are there, stabilized by resonance. Plus M means resonance, mesomeric effect. Okay, resonance is stabilizing this carbocation. So what is the option now? All cases, there is rearrangement. SN1 is possible and rearrangement is possible. Okay, done? Any doubt here? No, right? Very simple. Step by step, you check this. No. Next question. Among the given pairs, which pair compounds, in which pair first compound reacts faster than second compound? First one should react faster compared to second. We can do it very quickly, right? Because first break carbon halogen bond. That is the first thing. You have to make sure no you are breaking carbon halogen bond. Okay. So this will give primary carbocation here. Okay. But here it is secondary. More stable carbocation, more reactive it is. If carbocation is intermediate, right? So if it is more stable, so more reactive. More reactive, the reactant is more reactive. Rx is more reactive. Alkyl halide is more reactive. Okay. So what is the correct one? Primary, secondary. We can clearly second is dominating, right? Secondary carbocation is formed here. Second compound is more reactive. But what we have to find, first compound reacts faster. See, first compound reacts faster. Now see this will give tertiary, but this will give secondary here. No, first compound, right? Clearly this tertiary is dominating here. Direct. Here C option. So one single option, fine, B answer. But see this also. Here second is more reactive because it is resonance stabilized. Here there is no resonance. So okay. And second compound is more reactive. And see this one. Option D, how do we compare? Both are forming tertiary. Okay. If you break this carbon halogen bond here, no? Both of these will form tertiary. Both of these will form tertiary. But what we are comparing here, reactivity, which reacts faster means leaving group ability. Leaving group matters. Yes. Okay. CI bond is weak. CI bond is weak compared to CBr. We're comparing with CBr, not with C. Okay. CO or CF. We are comparing only these two, CBr and CI. CI bond is weak, so that reacts faster. Clear? So only one correct option, option B. Any doubts here? Okay. 1 second. We'll go to next question. Right. See this question now. Very, very important model. Till now we have done no SN1. Look at SN2 reaction. What is SN2 reaction? See, we'll quickly revise SN2 reaction means. SN2 means same substitution nucleophilic, but it's a second order reaction. Okay. So this reaction rate depends on what? Constant into second order reaction, nucleophile concentration, and also alkyl halide. It depends on both. Okay. Next, SN2 reaction, is there any rearrangement? No rearrangement because there is no intermediate. It is a single step reaction. Okay. It is single step reaction and there is no intermediate. There is no intermediate, no carbocation here. Okay. If there is no intermediate, obviously there is no chance of rearrangement here. Okay. no intermediate, no rearrangement, no rearrangement. Okay, and see this, one of the most important here, solvent effect. Okay, solvent effect means polar aprotic solvents favors SN2 reaction. What is polar aprotic means? Like DMSO. See, this is polar aprotic. This is polar solvent, no doubt. Polar means there is significant dipole moment, but hydrogen is not connected to oxygen, or hydrogen is not connected to nitrogen. So hydrogen is not connected to these elements. Okay, so that is what polar aprotic solvent means. Okay, polar aprotic solvent means. Okay, and also alkyl halide structure. Primary is more reactive than secondary, is more reactive than tertiary. If it is primary, there is no repulsions, directly nucleophile will attack. So these are the points for SN2. So we have to keep these points in mind to solve this question. Try this, no? Option A. First, what is the question here? The second reaction is more reactive. Today questions are lengthy, okay? Because option wise we have to check for reactivity. Second reaction is more reactive than first. First reaction, second reaction, so see this, no? First reaction, CH3CH2O minus and OH. Rest everything is same. And which is strong nucleophile? We can compare this, right? CH3O minus gives, this is greater than CH3CH2OH. Yes, sir. Are you sure? Because negative charge is present, that is more nucleophilic, more reactive. So option A, first reaction is more reactive. And look at option B. Look at option B and tell me. What we have to compare, ETO minus, ETS minus, which is more reactive? O minus or S minus? Okay, second one, ETO minus and ETS minus. Can you tell me now? Oxygen and sulfur, which gives electrons easily. Nucleophilic means ability to donate electrons, ability to give electrons, which gives electrons so easily. Here we are looking at ease of giving. Means if it gives easily, faster, nucleophilicity is more, strong nucleophile. So oxygen will give or sulfur will give. Both are minus charge. If one is minus, other one is neutral, no? Only negative charge can easily donate. But here both are negative. Oxygen and sulfur, which is greater nucleophile strength. You know, oxygen, sulfur. Which one? Sulfur. Okay. Sulfur is more, S minus. Negative charge is very stable. Oxygen is more electronegative, right? So it will stabilize negative charge. It will not, it doesn't want to give electrons. So option B, ETS minus. Fine. Next, so option B case, second reaction is more reactive. C option, this is 2 mole, this is 1 mole. More is a concentration of nucleophile, more faster. So concentration of nucleophile is more here. So first reaction is more reactive. PN, and there is no negative charge. See this, there is no negative charge. So clearly, if there is negative charge, we compared. But if there is no negative charge, N is more reactive. N is more reactive or P is more reactive? Tell me. Achha, there is no negative charge. PPH3 and PH3, PPH3. phosphorus and nitrogen we are comparing, both carries no electron pair. Which one? Phosphorus and nitrogen. Nitrogen is more electronegative. So first reaction is more reactive. Yes, like sulfur, no, like phosphorus. Because oxygen, sulfur, nitrogen, phosphorus. See, down the group, electronegativity decreases, their ability will increase. Okay, so only one correct option, where second reaction is more reactive than first reaction. Okay. Option C. Option C I am explaining. Concentration of nucleophile matters. 2 molar it is. Okay. See, look at this. This is 2 molar, 1 molar. More is a concentration, more faster this reaction is. Nucleophile concentration. Okay. Fine. Next question. Now coming to SN1, SN2, we discussed elimination reactions. E2 reaction is just like SN2, but there it is substitution, here it is elimination. See, E2 is a single step reaction. E2 reaction is a single step reaction. So what is the criteria for E2? Groups must be anti. Suppose if it is removal of H and X, okay, H and X, H and X must be anti. Or X and X, if you are removing 2 halogens, they must be anti. In most of the cases, okay, 99.9% they must be anti. But in bicyclic compounds, no, they are exception. Bicyclic compounds, E2 reaction, but syn elimination. Anti means what? Opposite. These 2 groups must be in opposite direction. Okay, fine. This is a single step reaction. Okay, there is no intermediate. No intermediate. Okay, so groups must be anti. So we have to take care about this point also. Next, what else? This may favor Sagev. This may favor Hoffman. Depends on conditions. I'll tell you 2-3 conditions where Hoffman is favored. Okay, so listen carefully. In E2 both are possible, but Hoffman and Sagev. What is the difference here? Hoffman product means less substituted. Sagev means more substituted alkene. Sir, what is less substituted? What is more substituted? If I take butene, okay, so butene, this one butene, 1, 2, 3, 4, okay, there are hydrogens. How many substituents are present here? Other than hydrogen, anything is called substituent. Okay, one substituent only. This is one substituent. Okay, but see this one alkyl group. Okay, but see this one. This has 2 substituents. 1, 2, 3, 4. Second. Butene, 2 butene. But see here how many substituents are there? 2 substituents. Okay. Now, Hoffman product means less substituted alkene. Less substituted what? What is this? It is alkene. Elimination alkene is found, right? This is also alkene. More substituted alkene is Sagev. So when Hoffman is possible, see, look at 2-3 conditions here. Weak leaving group. Weak leaving group like fluoride. Best example, weak leaving group. And bulky base. Bulky base means bulk, means very big in size. No? If that kind of base is attacking, yes, Hoffman is major. And next, a bulky leaving group also. Bulky leaving group. So I'll give examples here. Okay. Bulky base is this one. tertiary butoxide is present, suppose. Okay, it's a very big base, 4 carbons and this. So bulky leaving group, bulky leaving group is, see, this is leaving group, N plus methyl, methyl. If this is the leaving group, okay. So in those cases, half men product is major. But in rest all cases, no, Sejif. So these 3 cases, half men we get. And also you take care of resonance. Yes. Don't forget resonance. Sometimes resonance may favor less substituted, but more stabilized by resonance. So these are the 4 cases. We get Halfman, otherwise we get Sejif, more substituted. So one by one we'll see. In the above reaction, maximum Sejif product will be obtained when? When we get maximum Sejif product? Sejif means, no, when there is very good leaving group, when there is very good leaving group, we get Sejif. Which one is very good leaving group here? Yes, no? Iodine. But when we get Halfman product, fluoride. So these are the concepts we discussed. No? See, look at this carefully. These are the conditions. Okay, so we have to check all these 4 conditions so that we get Halfman product. If these are not there, there is no bulky base, there is no bulky leaving group, there is no fluoride leaving group, then we can clearly say that is Sejif product. Okay. Done? Right. See. Next question. Now look at this carefully. E2 reaction, just now we discussed, no? What is E2 reaction? These groups must be anti. See, remember this, no? E2 groups must be anti. Whatever you are eliminating, suppose if you are eliminating H and X, they must be anti, or 2 halogens, they must be anti. So based on that, this question, okay, you can solve. How to solve this question? This is Fischer projection, no? This is Fischer projection. When you write horizontal lines, vertical lines, this is Fischer projection. And alcoholic KOH, whenever there is alcoholic KOH is given, no? So this must be dehydrohalogenation. This is a trick, no? Alcoholic KOH is given means it is strong base. This will undergo dehydrohalogenation, means removal of HX minus H and X. So H and Br are the same side or opposite side? Can anybody tell me now? H and Br are the same side or opposite side? They're same side. Yes or no? They are same side. So now what I'll do, E2 reaction, they must be in opposite direction. But how can we bring this in opposite direction? Very simple trick, I'll tell you. Very, very simple trick. Okay. See, in any Fischer projection, look at this. This is called chiral center. No? This red color, no, center. This is called chiral center. So there are 2 chiral centers, chiral carbons. Okay. Now I need H and Br must be opposite. Sir, can we bring this opposite? Yes, because carbon-carbon rotation is possible. You're not breaking any bond here. You can rotate, no? You can rotate the bonds, fine. But you have to make sure the configuration doesn't change. Configuration should not change. But how do we change that? Okay, see, do complete rotation here. What is complete rotation meaning? This is a simple trick. Do complete rotation. Br you bring here, pH bring here, CH3. What you are doing here? See, I'll write this configuration without changing configuration. I just rotated carbon, CH3. Okay, H, pH I kept same, but Br is coming here. No? Br is coming here, pH is coming here, CH3 is coming here. Done. Okay, so in Fischer projection now, this has identical configuration. So what you can do is very simple. Well, tell you, these are organic molecules. See, you are standing, no? You are standing and looking at your classroom. Suppose you are in the classroom. Assume you are in classroom, or you are in front of laptop or mobile. Okay, you are just standing there, and left side, left hand, right hand, right? If you turn left side, what will happen? You are rotating, right? You're just rotating. Okay, what you're doing is you're just looking at your camera or whatever, laptop or mobile. Okay, but you take left turn, a right turn, that's it. Okay, by taking left turn or right turn, our left hand always will be left side. Okay, right hand always will be right side. They can't shift, right? You are not breaking your hands and making adjustments, right? Same thing here, you're not breaking any bond by rotation, and this is complete rotation. This doesn't change configuration. Okay, one complete rotation you do, this will give, same molecule, these are identical. Okay, this given molecule and these are identical, but H and B are now opposite. We need this for elimination. I am eliminating this H and Br. Now tell me, what about pH groups? pH groups, Acha, you can call it as even number of chiral centers, even number of changes at chiral centers. Yes, that is true. Okay, two changes we are doing, fine. But one complete rotation, you assume like that. With at any chiral center, one complete rotation gives identical configuration. Okay, pH and pH. One is horizontal, one is vertical. They are opposite. They are opposite. See where they're opposite, and both of these carbons, no, you see this is carbon, this is carbon. These carbons are connected to pH CH3 groups. So this option A you can eliminate, no? pH are not attached to same carbon here. Carbon attached to pH group CH3. So this is also not correct, because pH CH3, pH same side, which is not possible. But see, pH opposite side. Yes, option C. Okay, E2 means anti-elimination. This is always anti-elimination, 99.9%. But 1% case comes, no, where in bridged bicyclic compounds, syn elimination takes place. But they are not in the syllabus, don't worry. What we do is very simple: cyclic compounds, monocyclic, and or open chain. So focus on anti-elimination only. Try this one. Very, very important. Okay. Can you try? What is A? What is B? What is C? Very interesting question it is. How they are related? Are they equal or different? How it will be? Okay, fine. Let us see one by one now. So what is the case here? Dehydrohalogenation, I told you, right? 3 moles of KOH. 3 moles of KOH. 3 moles of KOH. See, first one I'll do. Let me do first one. Cl here, alternate. So I'll start with this one. Cl, H. One H is opposite, no? Okay. And Cl here, and this bond is H. Okay. And Cl here, this bond is H. Okay. So I will remove this HCl, this H and Cl, this H and Cl. Alternate. So what I can make is, I will get this double bond. One Cl is removed here. Now Cl. There is no need to write up down here. No, this is double bond. So don't write anything. Up and down is not required if it is sp2 carbon. So there's double bond here. There is Cl. Okay. And there is a double bond here. There is Cl. And look at the Cl positions. Where are they? If you start from here, 1, 2, 3, 4, 5, 6. 1, 3, 5 position. Okay, done. Fine. So what we get in reaction to? What we get in reaction to? A and B are same, right? Exactly, no? A, B, C, all should be same. See, we'll get same thing here. You see one by one, no? One up, one down should be there. If chlorine is up, hydrogen should be down. Okay. And see the same trick, no? So look at the same trick. H, no? Cl, there is H. Okay. And this Cl, there is H. And see, you are getting same molecule. Okay. H and Cl, yes, I removed H and Cl. This also I removed H and Cl. This also. Sir, do we need to write again up and down? No, it should be same. It is same. I'll write same. Okay. A equal to B equal to C equal to same. This 135 trichlorobenzene. You got the clarity now? Okay. It should be same. And start here also. Here I'll show you there is hydrogen up, no? And this Cl, there is hydrogen up. Remove this Cl, hydrogen down. 3 moles maximum. HCl removed. Okay. Again HCl removed. Okay. HCl is removed here. And there is HCl. All are dehydrohalogenations because alcoholic KOH in all cases. They must be anti. So the major point is here. Alcoholic KOH wherever you see. So that must be E2. Okay. Anti-elimination. Clear? All clear. Okay, done. Right. Next question. See this. Now, elimination, we did questions, no? Substitution, we did questions. Now, competition between E1 and SN1. Competition between E1 and S1. See, look at this. Br is present here. Okay, Br is down. And what is, there are some products given. So they are asking, what are missing products here? And it is given H2O ethanol and competition between E1 and SN1. Both are first order reactions. Carbocation is intermediate, no doubt. Okay, carbocation is intermediate, but this may be elimination or this may be substitution. This might be elimination. You have to assume both. Okay, and what is a missing product? Means what are possible products for SN1 and even both? You have to take care of rearrangement also. Okay, so I'll write first intermediate, then I'll ask you, okay, what is intermediate? You remove bromine. Okay, remove bromine. So what I'll get? This is what I'll get. Br means there's a positive charge. Wherever there is positive charge, sp2 carbon, no need to write up and down. Directly write methyl. Methyl, and this is CH3, okay, CH3 and H plus charge. Now this is our intermediate. Okay. If there is carbocation, now water can attack, no? Very simple. If I take substitution first, let us take SN1. Okay. This can attack from up or from down, both the directions. Both the direction. Now don't change this chiral center. This will be as it is. But this position, no, water means OH will come either up or down. Okay, either up or down. See, I'll write both. Both are possible. No? OH here, CH3. This must be CH3 and this is H because carbocation is planar, right? And this is down OH3, up CH3, and there is CH3 and there is H. So missing product is clearly what now? Substitution. One is missing product. Yes or no? One is missing product. One of the missing product. Now you can eliminate the options also. 3 and 4 no. 2 and 3 no. Because this doesn't contain 1, right? Understood? This is not containing 1. Clear? 3, 4 is not correct. 2, 3 is not correct. Either 1, 2, 3 or 4. You have to check 4 only now. Because only 4 is the difference, right? Let us check 4th one directly. Let us check 4th one. 4th one is elimination, right? 4th one is elimination. So these kind of questions you have to do logically, means eliminate the options and check, because it will take a lot of time. It will consume a lot of time. CH3, there is CH3 and H. So now, whether this product is possible or not, that is a question, right? This is tertiary. This is tertiary. Will it undergo again a rearrangement to get this secondary? Tertiary to secondary, is it possible? So I'll shift one of the hydrogen. Let me shift this red color hydrogen. Okay, there are 2 hydrogens basically. One of the hydrogen I shifted. So will I get this or not? Tertiary to, if I get carbocation, then I'll get alkene here. If it undergoes rearrangement, very simple logic, no? If I get rearrangement here, no? Yes, I'll get, but do this rearrangement possible? Is it possible? This is tertiary carbocation. We just discussed about all this, right? Secondary carbocation. Is this possible? No, right? Tertiary to secondary is no, not possible. Secondary to tertiary, fine. So 4 is not possible. 1, 2, 3, all are correct then. So 2, 3 elimination products, yes, they're possible. See, now after getting tertiary carbocation, you can eliminate this hydrogen, or you can directly eliminate this hydrogen or this one. You will get alkenes, right? You get alkenes. Both are possible. B, C, 2 and 3 possible. So 2 and 3 possible elimination. 1 is substitution possible because up, OH can be up, OH can be down. So 1, 2, 3. See this again. Any doubt here? No, right? Shall we proceed to the next question then? Okay, done. Next question. See this now. Number of products. Here, there are missing products we identified. We have done substitution. We have done elimination. See, you have solved all these like questions in different models, right? So now you should be able to solve any of the question from SN1 or any of the question from E1, E2. Should be ready to solve any type of question on E1 or SN1. Re2 or SN2, or substitution versus elimination. Look at this. Total number of substitution and elimination products. We have to consider substitution. We have to consider elimination. Both. How many we get? What we do? We have to break this. Means it is alcohol, right? Alcohol means SN1 and E1 possibility only, not SN2 and E2. It is secondary. Okay. SN1 and E1 possibility. So just check. So what we get here? This will give carbocation first. Okay. So I will write, two products which are with substitution. Okay. SN1 mechanism. SN1 mechanism. What product I'll get? Let me write those products first. Okay. There is CH3. Okay. There is CH3. But what about nucleophile? This is carbocation, so this can be down OCH3. Yes, possible. Or up, up OCH3 or down OCH3. Up means thick line, down means dotted line. Or you can say like towards observer, away from observer. So two possibilities for substitution. Is there any other product? No, right? Only two. Because secondary. Again, you can't shift to this position or this position, this position or this position, but again becomes secondary. Only look at the second, next position, next carbon. Don't look at the third carbon or fourth carbon. Okay, just look at adjacent carbons. Is there any rearrangement? No, because there is no extra stability. No extra stability. So two products are there, SN1. So what about elimination reactions? Elimination means what? You have to remove hydrogen, right? So this is positive. This is CH3. I'll keep it like this. Now E1 elimination. E1 elimination. I can clearly see there are two types of hydrogens here. This is hydrogen blue and this is hydrogen red. If I remove, I'll get different products. See this? Only alpha hydrogens, adjacent hydrogens only. Don't remove from any other carbon. Okay, only adjacent hydrogen. So this is CH3. Okay, and there is double bond over here. No? Double bond here, green one. And there is red hydrogen is as it is. No? And see this. If you remove red hydrogen, red color, so I'll get double bond here and there is hydrogen here. CH3 will be as it is. Sir, are they different? Yes, definitely are they different. See, look at methyl position from double bond. They're different, right? Methyl position from double bond. So this is what type of reaction? E1 reaction. Yes. So 2 plus 2, 4. Any other product? Do we get any other product? No, right? Because there is no further rearrangement. Carbocation stops here. It will not become any tertiary from this. So total 4 answer. So 2 plus 2. 2 substitutions plus 2 eliminations. Understood? Okay, fine. Next question. Okay, so this question is about reduction and reduction with very strong reducing agent, lithium aluminum hydride. Okay, lithium aluminum hydride is one of the strongest reducing agent. This reduction must be carried out with super duper, means most carefully. Utmost care should be taken while doing reaction in lab. Right, we write very simple with pen and paper, but while doing reaction is very, very dangerous. You know why it is? Can anybody tell me why lithium aluminum hydride is more dangerous? In laboratory, this is very difficult to handle. Okay, this is usually performed at very low temperatures. Okay, and even no, after performing a reaction, no, how do we perform a reaction? We perform reaction in glass vessels, no, borosilicate glasses you might have seen in your laboratories, right? But while after completing reaction, we wash that, right? Any chemist wash that apparatus. If very small amount of lithium aluminum hydride is there, no, that undergoes explosion with water, because this contains no H minus that reacts with H2O. So this gives hydrogen. So it is very dangerous reaction. So even small moisture is present, explosion will take place. That glass apparatus will break. Okay, so very, very dangerous reagent it is. Now it is more reactive. Dangerous means it is highly reactive. It reduces all functional groups. It reduces acid. Okay, yes, it reduces ester. It reduces aldehydes. Okay, it reduces ketones. It reduces each and every functional group. It reduces alkyl halide also. Rx2 RH we get, yes, or elimination we get. So it is strong reducing agent. See, this question is given because see, different functional groups are there: ketone, aldehyde, ester. So will it react or not? Will the student will be able to identify this or not? For that purpose, no, this question is framed. Ester, this is ester. Okay, this is ketone, this is aldehyde. All of them will react. All of them will get be reduced, right? Okay. So that is why, no, when you are a fresh chemist, when you are doing PhD or any post graduation, no, nobody allows you directly to do LAH reactions, and ozone analysis also very, very dangerous reaction. It looks very simple, right? Ozone analysis in organic chemistry, we break double bond, we put oxygen, oxygen, simple. But in laboratory, it is very dangerous to deal with ozone analysis. That ozonide particularly formed after reacting with ozone and hydrocarbon is very dangerous. Okay, so no fresh chemist or no fresh student is allowed for these reactions independently. Okay, one senior has to be there, one guide has to be there to monitor the reaction. Fine, see, this all this will react, right? So all this will react, will give what? Will give alcohols, right? This will simple, ketone will give OH, yes, this will give OH. You break here and reduce. This is breaking here and reduce. This is direct, no, CH2, no carbon loss. CO carbon is not lost. Look at this, CO carbon is not lost, that is converted into OH. Wherever the CO group, that is converted into OH. Even amides will react. They're very difficult actually, but lithium aluminum hydride react with this. All functional groups you can see. Okay, so what is the correct option? Option C. Option C, they are reducing agent, strong reducing agent. Fine, next one. See this. Here you reagents are given. First identify the sequence, which is first, which is next, like that. Identify the sequence of these reagents. First one, is it right? 1 2 3 4. Acha. 1 4 3 2. Okay. 1 4. See, this is a product. What is happening here? Methyl alcohol is added. Methyl is added and also alcohol is added. Look at this carefully now. And see, first one, methyl magnesium bromide. Yes, that is true. So this will give no methyl magnesium bromide will give us H plus followed by H plus will give us methyl and OH. Okay. After this, no, fourth one, H plus and heating. What we will get is this alkene. And next step is obviously no KMnO4 cold dilute. This is, there is a reagent name, no? What is that? What is the reagent name? Cold dilute alkaline KMnO4. Can anybody tell me? No. There's a test for unsaturation, Bayer's test. That is Bayer's test. Okay, Bayer's reagent. So we can identify unsaturation. Okay, fine. After getting this, so one of them is tertiary alcohol. Yes, this is tertiary alcohol, but this one is secondary alcohol. Blue one is secondary alcohol. Only secondary alcohols will undergo oxidation with CrO3. Okay, fine. See this OH, but this secondary alcohol will give ketone with this. Done? Okay, fine. So option C is the correct answer. So in the next class, we'll again meet and we'll discuss more questions. Okay. So I hope everybody liked the session. So please share your feedback. Now we're ending the session. Okay. So we'll meet in the next class. Thank you. Thank you, everyone. Today's session, you liked it. Thank you, Nishant, Srilekha, Kirtana, Isha, Ashik, Ramnathan, Kumar, Ganesh, Akshini. Thank you, everyone. You are attending regularly, right? I can see your names. VVSN, thank you, thank you. Arya, can you explain the question once more? Acha, acha. See, look at this. No, we are getting here 2 oxygens. That is a trick. 2 oxygens here. How to get 2 oxygens? In the middle, KMnO4 must be there, because KMnO4, we should know the role. No, this is diol. This gives diol with alkenes. Okay, so that diol gives, means one is secondary, one is tertiary, because only secondary alcohols gets oxidized with CrO3. CrO3 can oxidize secondary alcohols only, not tertiary alcohols. So that blue color one is oxidized, tertiary, there is no change. Okay. Is it clear now? Arya. Dibal H reduce. No. Dibal H is specifically, Nishant. Therefore, 2 groups. One is no RCN, RCOO dash ester. So both we can convert into aldehyde with dibal H. Dibal H, what we are doing is we are adding isobutyl groups to reduce the reactivity of hydride. H minus we are adding, but we reduce the reactivity by making it more repulsions, by adding more big groups, isobutyl groups. Okay. Yes. Thank you. So we'll meet in the next class. Stay safe. Stay home. Okay. Bye.